So enough about disaccharides. We're better than that now. We need to upgrade. And we're going to upgrade to now a polymer. And a polymer, of course, means many units. So that means many sugars are involved in these structures. And this is our first polymer that we're going to see. And this is called amylose. And it's a component of starch. It's the storage unit basically in plants. And if you notice, the stories here with polymers are no different than they are with disaccharides. The only modification that we've made is that there's more than two sugars now that are hooked up together. You've got multiple sugars that are hooked up together. Hence, that is why in this diagram you are basically seeing this oxygen connected to an imaginary bond. There's nothing there, right? Okay, well, that's a sign that it actually continues on over and over and over and over. And then down here at the bottom, the same thing is going to hold true here. This oxygen's pointed out to a bond. Typically, that would understood to be a CH3, but in the world of polymers, that's understood to go on and on and on. The way that you would know that this would go on and on and on in the polymer world versus a CH3 group at the end is that they would put brackets around this structure. So you would see typically a bracket drawn to the left and a bracket that was drawn to the right, and this bond would basically point kind of out of the bracket, and this bond would point out of the bracket. So that lets you know that that is not the entire molecule at all. The bracket is a representation of a polymer, and everything inside the bracket is what gets repeated over and over and over and over. So this is just another description or another way that we can draw a polymer and look at the individual sugars that make them up. If I look at this glycosidic bond, however, this glycosidic bond is basically the same as it always has been. You know, you take a look at the first unit here. Well, that's the anomer carbon, so that needs an alpha or a beta. Well, the bond points down, so that means that this is the alpha version, and it's on my anomer carbon, so that's understood to be 1. So we see alpha 1 that's listed there for the first half of the glycosidic bond. Well, the second half of the glycosidic bond, here's my first carbon, there's my second carbon, this is my third carbon, and this is my fourth carbon. So that is why this is an alpha 1,4 bond. So amylose has a alpha 1,4 prime glycosidic bond that is devoting itself to the structure. And that's how we determine it. It's no different than any of the disaccharides. This is the exact same thing as we've always done, right? We're just looking now at more than one bond, and that bond is repeating over and over and over. So if you look at this glycosidic bond, the same thing's happening here. This is also an alpha 1,4 prime bond, right? This is the alpha 1 and that's the 4 prime. There's no difference in the bonding as far as amylose goes here in the structure. It's repetitive. It happens over and over and over and over, and that is why we call it a polymer, because it's many units and they're all structured the same way. So that's the structure for amylose, component of starch. Very easy yet again. The thing that I want you to keep in mind, though, is that sometimes they like to throw a little trick. So on a sheet of paper, you notice that we like to clearly draw the OH groups down or up, right? And that's not really how they look. I mean, if you use ChemDraw, if you use some kind of software to draw these structures, well, they're not going to draw the OHs perfectly down and perfectly up. We do that because it helps us kind of visualize the structure and clearly defines whether this OH group is to the left or to the right. However, if you take a look at this structure, they're not clearly drawn straight down and straight up as far as the OH groups go, right? I mean, I'll take a look at this OH group. That's not straight down or straight up. And this OH group, that's not straight down or straight up. And furthermore, The actual ring itself, we've been kind of drawing like a hexagon that's been flat. Well, we need to understand that that is a ring, and rings tend to not be flat, only when they're aromatic, and this is not an aromatic ring. So this ring does have some shape. It is in the chair conformation. So because we have a chair conformation, we have axial and equatorial bonds. Axial bonds go straight up and straight down. Equatorial bonds go slightly out and up and slightly out and down. Now, if the OH groups have to be on a bond, they prefer equatorial if they can be there. So the reason for that is because it lets the molecule again spread out its wings and cover more ground, and there's more stability there. If it puts the OH group on an axial position, it's kind of like waving the white flag to come and say, hey, come and take my OH group, it's free to go. And the molecule doesn't really want to do that at all. So stability, equatorial bonds if it can help it. So that means in some of these problems, you might have to go back and review what the chair conformer was and the axial and equatorial bonds. Just note that here, this OH group, it's slightly pointed up, right? So even though it's not drawn completely up, we would still look at this OH group and say that is in the up position. Well, the axial position would go straight down here. So that's what you need to keep in mind when you concern these rings. My advice is to go back, take a look at some of those early on axial equatorial bonds that we saw back in the day of alkanes, and that was probably chapter 3 or 4 in your textbook. That's how early on we saw it. And just get yourself comfortable with the idea that if you do see a structure like this and you're basically asked to tell me what kind of sugar that is, well, know that equatorial goes slightly up and slightly down, and axial goes straight down and straight up. So that's what you need to keep in mind when it concerns these rings that are drawn in the chair position. Very, very important. So here's another polymer, and this polymer is a little bit different than the previous. This is amylopectin. It's the second component to starch. So starch is made up of more than one polymer unit, and this is kind of the second component. We get branching that happens every 20 to 30 glucose units. So this is glucose, and glucose is getting stored up in the plant, and when glucose gets stored in these long trains, well, it can come to you in the form of amylose or amylopectin. This is amylopectin. So what we see down here at the bottom is basically amylose, right? This is what we saw previously on the other slide. So this is amylose here, chain, 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 chain all the way down. The difference between that and amylopectin is that every now and then, every 20 to 30, kind of random, we see basically a branch that shoots out of this long train that's coming through the town, right? So this is the long train, and every 20 or 30 cabs of the train, you're going to see a branch that happens. And then when the branch happens, well, you see kind of the amylose train happen again over and over and over and over and over. So again, think of a tree branch, right? This is kind of the main stem coming from the tree, and then after that tree branch hits, well, you get other little twigs that kind of shoot off in multiple directions. The same things happens here. Glycogen's the same. Glycogen is kind of what we store, right? And glycogen happens more often, though. It happens 8 to 12 units, not 20 to 30 units. So glycogen is branched a little bit more than amylopectin is. This is a glycosidic bond. This glycosidic bond happens at carbon number 1 of this sugar. That's the anomeric carbon that's pointed down, so that's why this is called alpha 1. And then if it looks at this sugar, this is the anomeric carbon here, so that would be carbon 1. And then this is carbon 2, carbon 3, carbon 4, carbon 5, and then here is carbon 6. So that's why this is an alpha 1 6' glycosidic linkage. So amylopectin and glycogen are very, very similar. except glycogen branches a little bit more. So this is a representation of comparing amylopectin to glycogen. So amylopectin you see is much cleaner, right? I mean, you see kind of a train that goes through and then a branch happens here and there every 20 to 30, 25 to 30 sugars. Glycogen, however, is a little bit more compact, and the branching happens a little bit more. So this is the way that we store glucose for our energy needs. Your body goes through and begins breaking these little branches of glucose off and using it as it needs it. But this is the difference between amylopectin and glycogen. It's just simply the number of actual bonds that we see. Two other polysaccharides that we can talk about here, other than glycogen and amylopectin and amylose, is the difference between cellulose and starch. Okay, so cellulose and starch, once these polymers begin to happen, there are quite a few OH groups on those molecules. And the OH groups we have mentioned before participate in hydrogen bonding, and they're polar, and this is kind of glue that can help hold the molecule together and help prevent it from unraveling. The cellulose and starch are different, however. The cellulose is a structure that promotes intramolecular hydrogen bonding to generate linear arrays. Okay, so over here is kind of the representation of cellulose. Now, cellulose, again, think of plant, right? So cellulose, if I look at it, well, its three-dimensional structure is basically going to make it flat. And because it's flat, these hydrogen bonds participate within the molecule itself and they get kind of taken up. So cellulose is not water soluble. That's good news, because if cellulose was water soluble, what would happen when it rained? Well, all of your plants and all of your grass and all your trees would just melt away like the Wicked Witch of the Wizard of Oz, right? So we don't want that to happen. Cellulose is not water soluble, and that's good, because we don't want our plants and our nice kind of vegetables to melt in the water and dissolve. The starch, on the other hand, starch most of the time is helical in nature, and the helical nature of this basically frees up some of the OH groups, and these OH groups can then bond to water, and if they can bond to water because they're freed up, then they are soluble. So very often solubility is there when it comes to starch. And think of making your gravy in the morning or your gravy at Thanksgiving dinner. A lot of times if it doesn't get thick enough, what you do is you take some cornstarch, right, and you put it in some cold water in the beginning, and the cold water will dissolve that powder up, and it makes this kind of milky liquid that you then pour into your gravy and heat up, and then you kind of stir it and it gets a little thicker for you, so that way it's a true gravy and not a water. So starch is very water soluble, cellulose is not very water soluble. This is the structure of chitin. We mentioned chitin before. This is basically the hard shells on your crabs and crustaceans. So those of you that like to go to the Asian restaurants and get the buffet and the crab legs, keep in mind the crab legs don't come with the buffet. Most of the time you got to pay extra for them. But you can at least see the chitin that's there, and this is a very kind of hard sugar if you want to look at it, but this is a polymer of saccharide. The difference here is that chitin is a polymer. We see that beta linkages happen through here at 1 and 4 positions. Again, this points up, so that's the beta. The difference, though, is that the subunits here don't just have OH groups on them. They need to be slightly different because it is kind of a hard shell. So something kind of strange is happening here to the polysaccharide or the polymer. What happens is that these NH, double bond O, CH3 groups get added on. And that's the slight modification here that crustaceans have over other polymers like starch and glycogen and amylopectin. These groups kind of make everything a little bit harder, and it gives it a structural difference because of that. So cotton, same thing. It's a polymer of sugar, but the difference here is that one of the OH groups have been replaced with this what we call an N-acetyl amino group. So N, of course, is nitrogen, and acetyl represents the C double bond O CH3 group, acetate in a way, right? Okay, so that's the story with some of these polymers. We're just really taking a look at structural differences and the glycosidic bonds that happen in between them. Again, you don't need to memorize any of these, but you just need to be able to look at it and kind of identify them and talk about them and make yourself sound smart. So the next time you go to the Asian restaurant, tell the person that you go with, I know what that crab shell's made out of.